Okay, welcome on in. So this is module 12, week 12, and this is starting in on stats. So without further ado, let's dive into it. 12.1 from the book, sampling frequency distributions and graphs. So again, stats, right? We define statistics as a method of collecting, organizing, analyzing, and interpreting data, as well as drawing conclusions based on the data. The methodology is divided into two main areas. That is descriptive statistics, which is collecting, organizing, summarizing, and presenting data, and then inferential statistics, which is making generalizations about and drawing conclusions from the data collected. One has to be very careful with stats. Stats can be misquoted or used to mislead people, so it's important to know a little bit about stats, I think, for everybody. So, populations and samples in stats. A population is a set containing all of the people or objects whose properties are to be described and analyzed by the data collector. Right? A sample is a subset or subgroup of the population. So we might want to say something about the American voter. So the population is everybody in America, I suppose, who is registered or eligible to vote. To make the distinction, that would be something that the data collector would have to make, or the study would have to make. But the sample, you wouldn't want to go out and ask everybody who they're voting for. That would take you forever, right? So a sample is just a group of people that you would go and ask, who are you voting for, or whatever the question might be. And a representative sample is a sample that exhibits characteristics typical of those possessed by the target population. The distinction here is very important. I'm not going to get into anything political, but let's suppose we have a red party and a blue party running for president in the United States. And I go to an extremely red state and ask my 5 closest friends in that state, who are you voting for? That probably isn't going to be representative of the entirety of the nation. Likewise, if I were to go into a blue state and ask the first 5 or 6 people I come across there, who are you voting for? That's not likely to be a good representation of the nation as a whole. Right? So a representative sample, we have to go to great lengths to make sure that our sample is actually representative. Example 1, a group of hotel owners in a large city decide to conduct a survey among citizens of the city to discover their opinions about casino gambling. So the population is all of the citizens in that city, right? But again, this isn't something that you could go out and, I mean, you maybe could, but it would be a lot of work to track down every citizen of the city to find out what they think about this. And might be impossible because a citizen of the city might be away on business in Japan for 3 months and you have no way of contacting that person. If one of the hotel owners suggests obtaining a sample by surveying all of the people at 6 of the largest nightclubs in the city on a Saturday night, each person will be asked to express his or her opinion on casino gambling. Does this seem like a good idea? Right? And it's not, because those 6 people, all the people at 6 so the people at the 6 largest nightclubs, they're going to be a certain type of people, right? And there's no good or bad about that saying, but they're going to be people that spend their Saturday night at a nightclub. What you're not going to get is the opinion of the stay-at-home mom who's got 17 kids in the kitchen that she's got to feed, or all these other people. But you're narrowing down your view or your sample to a very specific type of people, right? And it may not be very specific, but you are being extremely exclusive with this group of people that you've chosen to interview. So a random sample. A random sample is a sample that is random. All right. It is a sample that's obtained in such a way that every element in the population has an equal chance of being selected for the sample, which means that mom at home with the kids, she has to be eligible and equally likely to be picked as part of the sample as the dude at the nightclub, right? So we have to go to great lengths to make sure that these people have the same probability of being interviewed, right? So there's many ways that we can do that. We can identify each element in the population. We can assign numbers to each element in the population, randomly select numbers, and then assign the elements in the population who have those numbers to the sample set, right? A lot of people call this picking a name out of a hat, right? Identify everybody in the city, every citizen, write their name down on a piece of paper, throw it into a hat, and pull out however many. That way, every single person in that hat has an equal chance of being pulled out. Let's go back to the hotel owners. The hotel owners in the large city are interested in how the city's citizens feel about casino gambling. Which of the following would be the most appropriate way to select a random sample? So option A, randomly survey people who live in the oceanfront condominiums in the city. Right? Already, you can just say that's a bad idea. Right? So many hotels, I guess this is the explanation here. Many hotels lie along the ocean front, and these people might object to the increased traffic and noise, which may result. It also does not give each citizen in the city an equal chance. So option B, survey the first 200 people whose names appear in the city's telephone directory. Right? And that's also not great because it doesn't give, you know, Henry Zesslinger a very good chance of being in this survey, right? So it doesn't give everybody an equal chance. It's just that first group of people, which is not a great random selection. And then C, randomly select neighborhoods of the city and then randomly survey people within the selected neighborhoods. And that's as best as we can get for these three options. It gives every citizen in the city an equal chance, right? Or equal-ish, right? But you would randomly select cities, right? Meaning don't handpick them, put the city name or the neighborhood in a hat and pull out those neighborhoods and then go and interview people in those neighborhoods. All right, so we're going to create a frequency distribution. So I have a bunch of numbers, right? This is the age of maximum yearly growth for 35 boys, and we have several values, right? We had 35 boys, they tracked them, and at age 12, 14, 13, whatever they may be, is where they were growing the most in their life. So what we've done is gone through and said, well, we're going to write out how many 10-year-olds we have on the list, and there's just one. How many 11-year-olds do we find in the list? And there's two, but I can't see the other one. There's the other one, right? And then we pick out how many 12-year-olds there are, and there's going to be 5 of them. So 1, 2, 3, 4, 5 of them, right? So really, we're just listing out the possible answers on the left-hand column and the number of those values on the right-hand column, right? And this is a frequency distribution. All in all, since there was 35, all of these numbers on the right-hand side should add up. If I take that plus that plus that plus that, all of these guys should add up to be 35. Otherwise, you've either missed some or accidentally overcounted, right? For a frequency distribution, if I look at this chart here, and we'll kind of go back and forth here, but or they actually list the information here. So the frequency distribution indicates that one subject had a maximum growth at 10, 2 at 11, 5 at 12, and so on and so on. If I look at this statement here, 9 boys experienced maximum growth at age 14, which is more than any other number. That's the biggest number here that we have, right? The sum, 35 is equal to the original number of data items. Like I'd mentioned, it has to be. So it really kind of shows that this one kid had maxed out at 10, some more kids maxed out at 11, and more at 12, and then even more at 13. So it kind of shows, for the most part, a growing trend until 14, and then a decreasing trend after nine students or nine kids that maxed out at 14, then it starts to decrease, 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 right? So it kind of shows patterns. It's not obvious until you kind of look at that, but we'll look at this another way. So let's look at another frequency distribution before we do. So we've got 40 students, and of these 40 students, we have stats scores, and they're all listed here. So rather than listing out every possibility and then counting how many of those there are, because these are spread, there may not actually be any that are duplicated, or if there are, it's going to be rare. I'm just kind of glancing over it, and I haven't spotted one that duplicates yet. There's 194 appears twice. So there are duplicates, but there's not a lot, right? There's such a big spread here. So rather than listing out every single value and saying, oh, there's one of these and one score here and one score here, we're going to put them in bins or ranges, right? So we're going to count up how many scores are between 40 and 49, how many are between 50 and 59, and so on, up to 90 to 99. There are no hundreds, so I don't have to worry about that. And I'm going to create the same kind of chart, the same kind of table that we created back here, but with this data and those bins. So it looks like this. So we call it a class. Sometimes it's called a class, sometimes it's called a bin. That's the same, same thing. Which class between 40 and 49, there's three of them, right? And if we can go back here between 40 and 49, there's one, there's one, there's one. There's three total, right? And they do that for all of them. The 50s bin or the 50s decade gives us 6. The 60s decade gives us 6. The 70s decade gives us 11. The next decade's 9. The next decade is 5. So I can kind of see this clear pattern here. There's a few here. There's more here, and then more the same amount, but more than the few. And then there's a lot perhaps here, and then there's fewer here, but the same kind of amount here, we'll call it more, and then there's fewer here, right? So we can kind of see that we start off with a few scores in the 40s, and then 50s gets a little better, and 60s stays about the same. But we get that jump up in the 70s, and then kind of a drop down for the 80s and another drop down for the 90s. If I want to look at this visually, we can actually see that in play, right? And to do that, we're going to look at something called a histogram. A histogram is a bar graph with bars that touch and can be used to visually display the data. So we had two frequency charts that we did. This one was the boys' ages at maximum yearly growth. If you recall, we had one student that maxed his growth at 10 years old, and then we had 9 students that maxed out their growth at 14-year-old. But this gives us a visual representation of what's happening with these numbers, right? This is the same chart. They just did what I did, but not smoothly, right? And it's much easier to look at this and say, hey, yeah, I can see the trend. There's a lot of these values in this middle kind of value, this 14. What they've done on this one over here is called a frequency polygon, which is just a line graph that is formed by connecting the dots in the midpoint of each bar of the histogram. A stem and leaf plot is just a plot that is constructed by separating each data item into two parts. So it's the tens digit, and then the stem is the tens digit, and the leaf is the units digit. Right? And it could be more. You could have larger numbers, but we'll just explain it with 2-digit numbers here. So I have, I believe these are the test scores. that we had before. I'm not going to go verify because it's not that important, but they might be because I remember there being 40s and there's 3 of them. But it doesn't matter. What I'm going to do is take each of these values and create over here. I'll start at the very lowest value in the 40s. So it's essentially the decade. In the 40s, I have a value of 43, 45, and 47. So each of these is listed as this way, as up to the 10s up here, and then the ones are listed here, right? Sometimes they put commas in them, sometimes they put spaces in them. It doesn't matter. But if I move to the next thing, the 50s, there was a 57, a 54, a 56, a 57 again. 1, 2, 3, 4, 5. And I think there's one more somewhere there, right? So I'm just going to put them in order here. 0, 4, 6, 0, 4, 6, 7, 7, 9. And we'll just keep going. And I'll not keep going because they do it here for you. So there are oh, okay. So they did this the first row. They just went through the first row there, which is fine. I'm just going through the entire thing in one go. So in the 40s, I had a 7, a 5, and a 3. They didn't order theirs. I did. It doesn't matter, but typically it's nice to see things ordered. For your stem in the 5s, I got 7, 4, 6, 7, 0, 9, which are the same values that I got. I just put mine in order. And so on and so on. We should end up with, in the 7 decades, we have 5, 6, 7, 9, 5, 3, 6, 4, 8, 1, 6. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 of these represented, which we saw that there was 11 when we did our histogram, right? Or our frequency chart. So there's a lot of things that can be done in these visuals to make them deceptive. So in this very first one here, this looks like this is just crashing, right? It's falling. Our US poverty rate, it's rapidly decreasing. That looks like a humongous crash. And look at this. Oh my gosh, if we just keep going in the next year, it'll be at 0. But no, right? This little thing right here, that little squiggle, means that that graph keeps going. So in reality, this graph keeps going all the way down here. And if like this is just 1% here, then 10.5, oops, knock it off. 10.5 to 9.5 to 8.5, 7.5, 6.5, 5, 4, 3, 2. This thing doesn't bottom out until like the bottom of the slide. And we're nowhere near 0, right? I don't know if I can undo that because I just drew all over this stuff. So cool. Very good planning on my part. But it's deceptive because it looks like it's getting close to 0. It's not. It's not getting close. It is falling, which is great, but it's not getting close to 0, right? Um, but if we rescale this thing, right? This is the same thing. It's a poverty rate. We're still starting at 13.5, starting at 13.5 here. But we've still got a bit of this thing that's missing, right? Means that 6, we're missing about 6% of this off the graph. But you can see this is a much slower looking decrease, but it's the same thing. The graph on the left here, this thing right here, this guy is the same as that guy. Let me try to find an eraser because it's starting to look. Where is my mouse? Eraser. Nice. There we go. Now it's less psychotic. All right. So the point here is that these graphs can be used to distort the underlying data. They can make it look like things are doing better or worse than they are. And then it explains why here. So things to watch out for in visual displays. Is there a title that explains what is being displayed, right? So a lot of times, it's not the case here. A lot of times you'll see a graph that doesn't actually state what is being, excuse me, displayed, and it could be something ever so slightly different, or not quite exactly what they're referring to in, say, the news article or whatever it is. Number two are numbers lined up with the tick marks on the vertical axis that clearly indicate the scale. And has the scale been varied in a way to create a more or less dramatic impression than shown by the actual data? Right? Number three, do too many design and cosmetic effects draw attention from or distort the data? And we'll see an example of this in a moment. And then has the wrong impression been created about how the data are changing because equally spaced time intervals are not used on the horizontal axis? Right? And I don't think they did that here. They didn't. But if you see something like, say, here's 2015, 2016, and then they just jump to like 2035 here, right? If that's not the same times difference between that and here, this is a bad graph. Alrighty. And are bar sizes scaled proportionally in terms of the data they represent? You might have, say, some data here that says the average age of, I don't know, a child of when they lose their first tooth, right? Might be that. And you might have, say, like males here, and then the next bar, I don't know if this is true. Don't take this as true. I'm just making stuff up as I go. But you might have then females, but if your bar is like that big, it makes it look like there's a huge difference between females and males if this is my female bar, simply because it's so much wider, right? It might only be the difference between here and here might only be 1 year, let's say, but it looks like there's a huge difference because of the thickness of that bar when it's has nothing to do with anything. And then six, is there a source that indicates where the data in the display came from, right? A lot of these false statements will come and say, oh, look, here's a chart of all my data. And then once you say, well, where'd that data come from? Oh, yeah, don't worry about that. Well, we're worried about that. If you don't have some source that we can go and fact check, then your data's garbage. Okay. So here's an example here. We've got this here, the data indicate, oh, just kidding, let's read it. So cosmetic effects of home with equal heights, but different frontal additions and shadow lengths make it impossible to tell if they're proportionately depict the given areas. So this is the number of square feet in an average US single family home. In 1740, we have some value. 1990, we have a value. These value, oh, sorry, 1980, the value was 1740. 1990, the value is 2080, and 2020, the value is 2392. So this is essentially the same home right here, pasted 3 times. But on the first increase here, they've just like thrown on this addition to the home. And it appears again in the next one here, but then they throw on this big garage, right? And I don't know. I can't tell what's going on with these pictures, right? I'm not a home adjuster. I can't say, yeah, that looks like it's a difference of 300 square feet. I don't know. I don't know anything about this. But they also threw the shadow on here, which turns this into like a not only a two-dimensional thing because of the face of the home, but also you've got this shadow. So you've got this wonky three-dimensional. Like I look at this and I'm like, what in the hell is happening with this graph, right? Show me bar graphs, show me true numbers. 1740 is that much, 2080 is that much, 2392 is that much. That I can tell what's going on. This, if my realtor came to me with this, I would throw it back at him and say, this is dumb, you're fired, whatever, redo it. So the time interval on the horizontal axis are also not uniform in size. So the jump between 1980 and 1990 is 10 years, but then from 1990 to 2020 is 30 years. So ignoring that, it looks like these are just, increasing linearly, and they're not. They're going to be increasing at a more like a logistic. You don't need to know that word, but it's not every year every house gets bigger. It's every, you know, now 30 years, every 40 years, these houses might get a bit bigger instead of every 10 years or sooner. Right? So that's it. Anyway, thanks for being here. Thanks for watching, and I will catch you guys for the next one.